All right. So as promised, we're going to do a little regression analysis here. First thing we're going to look at is our descriptive statistics right here. We've got an n of 100. So we've got a sample of 100 here. Now we're going to move on to this correlations table and see that we've got three predictors here and one outcome variable. And this tells us to what degree are the predictor variables correlated with both each other and then also with the outcome variable. We can see that they are fairly well correlated, or highly correlated with the outcome variable here, these two. This predictor is less correlated with the outcome variable, and perhaps more concerning is the fact that it is more correlated as a higher correlation with the other predictors. So again, multiclinearity becomes a risk in that scenario. The next thing I want to do is actually jump down all the way to the bottom, and I want to look at these partial regression plots. I want to check the how linear our data is, which is another assumption that we need to meet. And again, this looks fairly linear. It kind of fits a kind of an additive relationship there. The line right here. So that's our first predictor. Our second predictor, kind of similarly linear. Which is good. And then this one, less linear. Again, this is the one that I had a little bit of a problem with above with the correlations. Still linear though, still worth kind of interpreting everything else. I would say this assumption is still met. Moving up though, again, keeping everything in mind about that third predictor. So we're going to look at our R-square, which is going to determine the amount of variance that our model can account for within this outcome variable. So this variance of the outcome variable, how much of the variance does our model account for? 0.35 is pretty good. Definitely happy with that. It is kind of important to note, though, that Ozer talks about R-squared can actually undermine the strength of the relationship in the model. And in this sense, it may not be kind of the best thing to look at the effect. And Kirk actually agrees with this, that R squared is not really the best indicator of effect magnitude. And he actually suggests that we use the omega squared, intraclass correlations, and Cohen's F. So side note there, moving on, Durbin-Watson. It tests our assumption that our errors are random. A Durbin-Watson of 2 will indicate that they are random, and this is close to 2, which is good. If it's it's closer to 1, then it indicates that our errors are actually positively correlated, or I'm sorry, our residuals are positively correlated, and it will indicate that our residuals are negatively correlated if it's a little bit closer to 3 and 4. Again, it's from 0 to 4, but it's close to 2, so that's good. ANOVA here, we see our model is significant. That is definitely good, but again, we don't really need, we will be interpreting an ANOVA in just a little bit. So the next thing to look at here is the B. So again, this is how much of the variance can each individual predictor kind of account for. And the way to interpret this specific finding right here is that for every 1 increase in our outcome variable, our predictor will actually increase by 0.406. Again, pretty good. So then we're going to go over here and we're going to look at our significance. These two are below 0.05, so they are significant. Our third is not significant. Again, kind of keeping in mind that it is just not a good predictor, does not account for enough variance. It may also be because it's so highly correlated with these two that it's not capable of accounting for any more variance than what they're already accounting for. Moving on, looking at this confidence interval, which is very interesting, you can see that 0 falls between these two, this confidence interval, which would be our null hypothesis. Again, not what we want. We do not want 0 to be within our confidence interval. And this actually gets at some of the stuff that Avery was talking about in terms of reporting that essentially significance is not enough, and that you want to report the effect sizes and the confidence intervals. And Fidler actually kind of rips apart the APA manual and its lack of instruction on kind of how to do this, how to report these. Going over here, we have the partial correlations, which indicates how much of the variance is accounted for by each of our predictors once the others are factored out. Again, pretty good. And you can see here that, again, this is not accounting for really much. So we have the collinearity statistics now that we want to look at, and they're going to see whether or not the essentially predictors have anything in common with each other. And so here with tolerance, we want our tolerance to be above zero point 0.2, and as you can see, it essentially it is, which is good. And we want these numbers for our variance inflation factor to be close to 1. And for the most part, they are. It gets farther away here. Um, so now moving on to case-wise diagnostics, we specified that we wanted kind of a standard deviation. We wanted a kind of a window of 2 plus or minus standard deviation. So this helps tell us which potential cases are going to be outliers and fall outside of that window. So it looks like we have 5 to look out for. And this residual statistics, the big one to look at is that our mean residual is 0. Which again is another assumption of our model and regression assumption, and it is met, which is good. Now we're looking at the distribution of our residuals, and again we want a normal distribution. For the most part, this is a normal distribution, a little underrepresented here in the towards the mean, but that's okay. And we want to look at here as well, kind of the where our data lies. And it looks like it hugs this line of best fit pretty well, which is good. A little deviation here, but not really something that I personally would be concerned about. Again, meeting more of our assumptions. And here we can see kind of the the scatter plot will essentially tell us it's a test of homoscedasticity. So how random are our errors? We want them to be random. So we want this to kind of look like a cloud, and it does. It looks like a cloud, which is good. We don't want to see a lot of pattern here or anything like that. We do not want an arch or a funnel shape. And again here as well, same thing, and we have a cloud. So again, the random error or random the residuals being random is another assumption that's been met. And we saw the linear quality of our data. So that's about it. The next thing to look at is an ANOVA.